I'm going to start with some history, and this is the best maths student we ever had here in Cambridge. I'm afraid it's been downhill all the way for 300 years since him. But it's appropriate to start with Isaac Newton in this lecture, and to remind us that, as far as he was concerned, this was the universe. He knew about the planets, the 7 classical planets, and he knew that there were stars much further away, but he didn't know how far away nor what they were made of. But he famously designed his telescope, and I should have said also that he was the first unifier. He showed famously that the force that holds the planets in their orbit is the same that makes the apple fall and holds us down on the ground. This was his reflecting telescope, of which you could see the stars. And of course, the stars have been known since antiquity, but it wasn't until about 1860 that people realized what the stars were made of. Classically, it was thought they were made of some special essence, different from stuff on the ground. But it was this chap here, Sir William Huggins, who was the first person to use a spectrograph and to look at the sun and the stars and see spectral features. And he was the first person to realize that the stars are not only like the sun, but they're made of the same stuff as the sun and as the earth. There's nothing special about the material that makes the starry heavens. Newton also must have thought about space travel. This is an illustration from the English version of his book Principia. It shows a cannonball being fired from a mountaintop, and if it's fired fast enough, its trajectory curves downwards only as steeply as the Earth curves away underneath it. It goes into orbit. This is still, I think, the neatest way to explain the concept of orbital flight. But Newton realized that to go into orbit, you've got to fire your cannonball at 18,000 miles an hour, and that was not possible at his time. And as people here know, it was the Soviet Sputnik in 1957 which was the first object to go into orbit. And 10 years after that, we had this iconic picture of the Earth taken by astronauts orbiting the moon, the sterile moonscape contrasting with the Earth's biosphere. Well, I'm going to give you a very quick tour of the universe as we now know about it, starting with what we can do from space probes. People haven't been any further than the moon, but space probes have been to all the bodies in the solar system, giving us close-up pictures of them. And so if you go out in your space probe, and you look back at the Earth from about 5 million miles away, you see this. This is a picture, half Earth and a half moon. The sun's coming from the right. And then you get to the red planet. Here it is. And there are lots of probes that have been to the red planet and orbited it or landed on it. Here's some pictures they take. Here's another one. This is a gorge several miles deep. And this is the Curiosity probe that landed on the surface of Mars about 18 months ago. It landed where that little ellipse is in the top left of this big crater about 100 miles across, and it's trundling around. If you look very carefully, you can see the tire marks there along the bottom where it's been going. It's been about 30 kilometers so far, and it's eventually going to climb the mountain in the middle. And this is a view it's taken. Doesn't look all that exciting, but it's about the height of a person, so this is what you would see if you were looking on Mars. And this is another picture, and you can see the geological strata which it's going to be probing. Going out beyond Mars, the next planet we come to is the giant planet Jupiter, and it's got the 4 famous moons that Galileo discovered, and they've been observed close up. They're very different. This is Io, which is sulfurous and volcanic, and this is Europa, which is covered in ice, and there may be an ocean underneath it. And this is a close-up of the ice. It's clearly been melted and condensed many times. Then we get to Saturn. This is a picture taken by the Cassini spacecraft showing Saturn with the rings completely edge on. And this is a rather beautiful picture. This shows an eclipse of the Sun by Saturn. It's taken by the Cassini spacecraft when it's beyond Saturn, lined up at just such a distance that Saturn blocks out the Sun, but the rings are still illuminated by the Sun. And although you can't quite see it, the Earth is about where that arrow is. It's a long way away there. And light signals would take several hours to get to Saturn. And that's why it was very impressive when the Europeans landed a small robot on the surface of Titan, which is Saturn's giant moon. And the left-hand and center pictures show what this robot saw on the way down. It parachuted onto the surface of Titan, and the right is where it landed. This may look a rather nice place. You can see rivers, a little lake, but the temperature is minus 160 degrees centigrade, and those rivers are liquid ethane, so it's not a very salubrious place to live. I expect in the coming decades, robotic probes and fabricators will pervade the whole solar system, but I don't know whether people will follow. This is Harrison Schmitt, the last man in the moon in 1972, and we don't know when people will return. And for the youngest people in the audience here, it's ancient history when men walked on the moon. You know that the Egyptians built pyramids, you know the Americans went to the moon, but these both seem ancient history, motivated in both cases by strange national goals. And there was no motive to go beyond that. And in the question period, I'll say more about the manned space program, but let's move on. Well, people want to know, is there any life in our solar system? We don't know. There might be something swimming under the ice of Europa. There might be something on Mars, but no one expects anything very exciting. But when we look further afield, then prospects have opened up. One thing we've learned in the last 10 or 15 years makes the night sky much more interesting. We've learned that most of the stars you see in the night sky are not just points of light, they're surrounded by retinues of planets, just as the Sun is orbited by the Earth and the other familiar planets. These planets are not in general seen directly, they're inferred by precise measurements of the Sun, of the star they're orbiting around. And I'll just mention these two techniques, they're both very simple. The first comes from noting that if a planet's orbiting a star, then actually both the planet and the star orbit the center of mass, what's called the barycenter. The planet goes round in an orbit, the star, being heavier, goes round in a smaller orbit. But very precise measurements of the Doppler effect of the star can detect these motions of the star only a few meters per second, 10 to the minus 8 of the speed of light, due to an orbiting planet. And here's an example of showing the velocity towards us of a star over one cycle, and this is a sine wave indicating a planet orbiting in a circular orbit, and you can infer from such data the mass of the planet and how long its year is. And by this technique, many hundreds of planets have been inferred. But they're mainly big ones, like Jupiter and Saturn, the giants of our solar system. An Earth-like planet would induce a motion of only a few centimeters per second in its central star, too small to be detected by this technique. But there's another technique, transits. If you're observing a star and a planet whose orbit is in the plane of your line of sight, then whenever the planet moves across in front of the star, it'll block out a bit of its light. And so the brightness of the star will dip a little bit. And then it'll dip again when the planet comes round. And it's a small effect. If the Sun was seen from a great distance, then the Earth, being about 1% of its diameter of the Sun, 1 part in 10,000 of the area, will produce a dip by 1 part in 10,000 in the Sun's brightness. But the Kepler spacecraft spent more than 3 years observing an area of sky and measuring the brightness of 150,000 stars with a precision of 1 part in 100,000, over and over again, once or twice an hour. And it was looking for just these effects. And indeed, it found hundreds of planets, many no bigger than the Earth. And incidentally, some amateurs found planets, because it was possible for an amateur to get access to the time series of Kepler data on one star. And in fact, some amateurs found a planet orbiting a double star to be 2 suns in its sky. That's because the automatic algorithm didn't detect something like that. Well, these two methods are indirect. We'd really like to observe the planets directly, not just their shadows, as it were. And that's hard. To imagine how hard, let's suppose that some aliens with a big telescope are looking at the solar system from, say, 20 light years, the distance of a nearby star. The Sun would then look an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, like a pale blue dot. very close in the sky to its star, our sun, and billions of times fainter. Very hard to detect. It's like looking for a firefly next to a searchlight. But if the aliens had a big enough telescope, then they could learn something about our pale blue dot, because the shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing you. So they can infer there were continents and oceans, the length of the day, something of the seasons and climate, and maybe by looking carefully at the light, that there was a biosphere. Well, we can't do that yet, but within 20 years, or maybe 10, we'll be able to do this. In particular, with this instrument, which European astronomers are building. They're not very good at imaginative names. It's called the ELT, the Extremely Large Telescope. And it is indeed planned to be extremely large. The mirror is going to be 39 meters across, and that's, I guess, about twice the width of this lecture room. It's not just one sheet of glass, it's a mosaic of hundreds of pieces of glass. But instruments like that will be able to detect Earth-like planets orbiting other stars and infer a lot about them. This is a very exciting development. Will there be life on any of these planets? Well, that's another story. I'll say no more about it. Let me just say that biology is a harder subject than astronomy, and it'll be longer before we understand that than it takes us to understand the planets. Now, astronomers didn't realize that these planets existed until 20 years ago when the first one was found, and most were found within the last decade. But they weren't surprised. They weren't surprised because they've known for good reason that when a star forms, it goes through stages like this cartoon. This is an artist's impression. The star forms from a slowly spinning, dusty cloud of gas. As the cloud contracts under gravity, it spins faster, conserving angular momentum. And the protostar forms, and around it is spun off a dusty disk. And the dust agglomerates into rocks and then into planets. And this, we believe, is the way our solar system formed. And it's a generic process, so we're not surprised to find that planets are common around other stars. And again, flashback to Newton. This is what Newton wrote in his Optics. He, of course, famously understood why planets move in elliptical orbits, but he didn't understand why all those orbits were in the same plane, what we call the ecliptic, whereas comets come in all directions. He thought this was providence or something like that. But of course, we now understand this. We've pushed the causal chain back. And I mention this because that's what we're doing all the time in cosmology. We're understanding further back how the causal chain goes, and as I'll say later in this talk, we've got back not merely to when this solar system formed, even to when the first stars formed, but right back to the first tiny fraction of a second after the Big Bang. Stars are, in fact, quite well understood. As I mentioned, Huggins first showed what they were made of, and we now understand their evolution. We know that the small ones burn their nuclear fuel slowly. The big ones burn the fuel more rapidly and shine much more brightly. They're the blue stars we see in the sky. And they end their lives with remnants, white dwarfs, neutron stars, or black holes. And we see stars forming and dying when we look in the Milky Way. This is the Eagle Nebula, 7,000 light years away, where even now new stars are forming, like in that cartoon, and will form with dusty disks around them. Here are some stars dying. The Sun will look like this in about 6 billion years. Here's another star dying, throwing off its outer layers. And here's a more massive star that died 1,000 years ago. This is a famous object called the Crab Nebula, which is the remnant of a massive star which exploded as a supernova in the year 1054 AD. And that explosion was recorded by, I guess, the Chinese counterpart of the Astronomer Royal. And any Chinese readers here will notice, he says, that the star flared up to be brighter than the full moon and faded after a few weeks. And now when we look in the sky, we see the exploding debris nearly 1,000 years later, and this material eventually merged with interstellar gas. Well, these supernovae may seem irrelevant, far away and long ago, but as this man in particular showed, they are crucial to our existence. And this is why. If you were to take a slice through a big star just before it explodes, then it would look something like this, an onion skin structure, where the hotter inner layers are burned further up the periodic table. Hydrogen goes to helium, and helium goes to carbon, and to oxygen, and so on. And when the star runs out of nuclear fuel and faces a crisis, its core implodes, and the rest is blown off to make this explosion. And Fred Hoyle's wonderful idea was that this material eventually mixes up and new stars condense, like in the Eagle Nebula, and then makes stars like the Sun and the solar system. So every atom in our bodies of carbon, oxygen, etc., was forged in a star which lived and died more than 4.5 billion years ago. And the Sun then condensed from a gas cloud contaminated by debris from that earlier generation of stars. And indeed, careful calculations suggest that we have inside us atoms from many thousands of different stars, which lived and died all over our Milky Way galaxy. So we are the ashes of long-dead stars, or if you're less romantic, we are the nuclear waste from the fuel that makes stars shine. Fred Hoyle was the pioneer, but it's a famous paper by Burbidge, Fowler and Hoyle. There's Burbidge and Burbidge, husband and wife, they wrote this wonderful paper in 1957, which codified this whole idea of how from pristine hydrogen all the elements were made. This was actually taken in Cambridge for Willie Fowler's 60th birthday, and he was a train buff, and that was his birthday present. And this idea can explain the proportions. It can explain why there's lots of carbon and oxygen, why gold and uranium are rare, and how they came to be in our solar system. And they give us a picture that our galaxy is really a sort of ecosystem where pristine gas from the early universe makes the first stars, and that gas is just hydrogen and helium, and then that makes the rest of the periodic table, and then that's recycled into a generation of other stars, and our Sun was a later generation star contaminated by earlier generation. And this is going on in our Milky Way galaxy, which contains about 100 billion stars. If you could go 2 million light years away and look back at our Earth, we would see something like this. This is, in fact, the Andromeda Galaxy, our nearest big neighbor in space. It's about the same size, and it's a disk viewed obliquely. It's a circular disk where the stars are orbiting around a central hub, and our galaxy would look just like this if we could get 2 million light years away, and our Sun would be somewhere out towards the edge, orbiting around like that. Here's another galaxy. This one is looked at more or less face-on. And galaxies are the main ingredients of the large-scale cosmic scene. This is a map showing the galaxies within 500 million light years of us, and the galaxies are themselves in clusters, some clusters containing hundreds or thousands of galaxies. And we and Andromeda and a few small members are in a so-called local group, which is a rather small cluster. Well, I mentioned that we understood quite a bit about stars, and we even understand quite a bit about galaxies. And this might surprise you, because we seem pretty helpless. We can't do experiments, and they evolve very, very slowly. We can't do what a particle physicist does and crash together particles and see what happens. At least we can't do that in the real world, but we can do that in the virtual world of our computer. We can ask what would happen if two galaxies fell together and crashed. And here's a movie showing this. These two galaxies, and they're computing the gravitational effect of all the stars, and you get a sort of train wreck when they collide, and eventually all the stars will settle down, and we'll end up with one big amorphous galaxy, where there were once two disk galaxies. And we can look in the sky, and this is a real picture of two galaxies. And having done calculations in our computer, like the ones I showed you, we can infer that what's happened here is two galaxies have got dangerously close, and that one has pulled out a tidal plume on the other, and if we came back in 100 million years or so, they would have merged together. And I should warn you that the Andromeda Galaxy is going to crash into our Milky Way in about 4 billion years, 4 billion years. Not million, so be reassured. And so this is something which we can do. And we can also do calculations making different assumptions. We can put in different amounts of gas, different amounts of dark matter, etc., and see which fits best. And one of the things we have learnt about galaxies is that there's more to them than we see. We see lots of stars, we see lots of gas, but they contain about 5 times more stuff in some dark form, some swarm of particles that don't emit or absorb light. This is the famous dark matter. I don't have much time to go into this, but there's various lines of evidence. One line of evidence is if you look at galaxies in a cluster, then they're moving around very fast, you can measure their motions, and you can infer that the cluster would fly apart unless there was more mass binding it together than we see. That's the dark matter. And this chap here, Fritz Zwicky, he was the first person in the 1930s to actually realize that this was a big problem. The second technique for finding dark matter is that X-ray astronomers can observe hot gas in a potential well of a cluster of galaxies. And from its temperature, they can infer what its pressure is and how deep the gravitational potential is. And here's an example of an X-ray map. And from this kind of argument, you can infer that the gravitational potential of the cluster is due to more than the galaxies we see. And the third method, which certainly Einstein would have liked very much, which indicates its excess mass. That's illustrated here. The bright objects are galaxies in a cluster about 1 billion light years away. The faint objects are galaxies several times further away still. And you can see that some of those faint objects are elongated into arcs. What's happening is that the cluster of galaxies is acting like a poorly figured converging lens, because gravity bends light rays. And it's distorting and magnifying some of the background galaxies. And you could do the sort of optics and work out what the mass has to be in the cluster in order to produce the distortions you observe. And again, you find about 5 times as much dark matter must be there as in what we see. Now, the other important thing we have to realize about the universe is that when we look at distant galaxies, they're receding from us, they're expanding. This was a famous result of Edwin Hubble. He is a heavy smoker, as you can see. He was the first person to realize that distant galaxies are receding. The further away they are, the faster they're receding. And at first sight, people think this means we're in some special central position. But it doesn't mean that. And I'd like to illustrate it by imagining this network, which could go on forever, and supposing that all the rods lengthened at the same rate. Then if you sat on one vertex, you'd see the others moving away at a speed proportional to the number of intervening links. And that's a good way to think of the Hubble law. Imagine the galaxies joined together by rods. It's a good model, except that, as you saw, the galaxies aren't in a regular network. They're spread around in a complicated way. There's one feature that's not reflected by this picture and is better reflected by another Escher diagram, angels and devils. And that's because when we look a long way away, we look far back in time. And therefore, if the universe is expanding, we look back to a time when things were more compressed, when the rods were all shorter. So what we actually see when we look back is more like this picture, where as we look back in the past, things look more and more crowded. And we can look very far back. This is a picture which shows a tiny patch of sky. A patch of sky so small it would take about 100 like it to cover the full moon. It would look quite blank with a small telescope. But with a big telescope, you see here hundreds of smudges, each a galaxy, many fully the equal of our own galaxy or the Milky Way, and looking so small and faint because of the huge distance. Many of these are so far away that the light set out 10 billion light years away. So we're looking back very far. And these have a very big redshift. And I'll show you one picture. The very faint object there has had a redshift taken 2 years ago by this group, and this is just a tracing. And the reason I show this is that the strong peak, the strong emission on the left-hand side is the famous Lyman alpha line of hydrogen, which is normally in the far ultraviolet, 1216 angstroms. But here it's stretched in wavelength by a factor more than 8 into the infrared. So this is an object very far away. Incidentally, this is not a typical galaxy. It's a galaxy which has in its center a spinning accreting black hole. It's a quasar, and the quasar gives much more light and brightens the gas so we can see a clear picture. And so what's going on in the center of the galaxy is something like this, gas swirling in to a central black hole. But again, that's another story. If you could look even further away, further back, we'd look back to a time before there were any galaxies. But again, as I expect everyone knows, we do have evidence for what the universe was like at the early pre-galactic era. And most famously from this spectrum here, this was discovered 50 years ago, that the whole of space is pervaded by weak microwaves, which have the spectrum of a thermal radiation black body at 3 degrees above absolute zero. And this radiation is the relic of the universe's hot, dense beginning. The universe was once much hotter and denser than the inside of a star, and as it expanded, then the radiation got diluted, the wavelengths got stretched, and they shifted right down to the microwaves, and we're left behind with just this. And evidence of this kind and others has led to this standard time chart for our expanding universe. And we can look back, when we look back at the most distant galaxies, we're looking back to about 1 billion years. The microwave background photons were last scattered when the universe was 300,000 years old. We have fairly good evidence, actually, about 1 second, that's when nuclear reactions made hydrogen and helium and deuterium in the proportions we observed. So we've got confidence back there. But why stop there? If we go back to about a nanosecond, then every particle in the universe would have an energy equivalent to what you can produce at CERN in Geneva. Further back still, it becomes more uncertain. But at a nanosecond, everything we now see with our telescope out to those distant galaxies would have been squeezed down to the size of our solar system. I'll say more about it in a moment. But one thing which people often ask when they're presented with this idea is, doesn't it seem contrary to the famous second law of thermodynamics? Because we say the early universe was amorphous, a hot fireball, and now it's structured with galaxies, stars, and us. Doesn't this seem contrary to what the second law is supposed to do to wash out structure? Well, the answer is that gravity has funny properties as far as thermodynamics is concerned. If you have the early universe not completely smooth, but some regions a bit denser than average, then as the universe expands, those dense bits will lag behind more and more, and eventually will condense out. And this movie shows a region of the universe, and the expansion is subtracted out. But you see early on the density contrasts aren't perceptible, but as it expands, then the overdense regions lag behind more and more. And I should say that the blue is the dark matter, the red is the atoms, which are going to make the stars. So this is how a galaxy forms from an initial slight overdensity in the early universe. It's not contrary to thermodynamics, it's just that gravity enhances density contrasts, doesn't wash them out. And this story has a lot of corroboration, because when we look at the background radiation, we can observe how smooth the universe was when it was 300,000 years old. That's when its radiation was last scattered. And this famous picture from the Planck Satellite shows the fluctuations. The scale is amplified, but some patches are warmer than average by 1 part in 100,000, some are cooler than average by that amount. And the important point is that in the simulation I showed, the fluctuations initially weren't put in at random. They were put in from here. And it's a great vindication of this idea that the fluctuations observed when the universe was 300,000 years old, under the action of gravity, will develop into structures which match what we see today. And this is one diagram due to Max Tegmark, which summarizes all this. The theory says that the density fluctuations, root mean square, on different scales should follow this line. And we have lots of data looking at galaxies and clusters, etc., and they follow pretty well. So the idea that the early fluctuations seen in the microwave background are the seeds for all the structures we see is strongly vindicated. So there's a step-by-step emergence of complexity. And I've talked about gravity forming the first structures, but it's fairly clear that other things had to happen, because the steps that led to us involved forming stars, heavy elements, etc. And what I want to do now is to say something about what the prerequisites are in getting from a simple beginning to us. And the reason I'm going to do this is that we can then ask, suppose you tweak some of the numbers. Would this change things? I'm going to end up by saying maybe there are places where the numbers are different, but for the moment, if you don't like that idea, you can reassure yourself. It's just like, you know, about counterfactual history, where people ask what would happen if Britain didn't fight the First World War, if the Brits behaved better in 1776, or if an asteroid didn't wipe out the dinosaurs, etc. It's counterfactual history, and you can ask in the same spirit, what would it be like if the universe evolved differently? Well, what are the prerequisites? The first important one is gravity. I mentioned it's important in enhancing density contrast to make the first stars and galaxies, but it also, of course, holds together the stars. I'd like to put this up. This is my favorite pedagogical diagram. It shows radius along here and mass up here. And there's a proton, and there to the right, that's an atom, roughly the mass of a proton, and larger by the fine structure constant to the -2. That's about the raw radius, 10 to the -8 centimeters. This is a black hole line, slope 1 on a log-log plot, and the black hole with the size of a proton has a mass of 10 to the 38 protons. That reflects how weak gravity is. Now, if you take solid objects, then they're roughly the density of one atom per unit volume, and you can imagine building up sugar lumps, people, asteroid, etc. And this is getting close to the black hole line. It can't go up forever. And what happens is that an asteroid isn't affected by gravity. Then you get to a planet, gravity can make it round, and you get up to the mass of Jupiter, then gravity can not only make it round, but can start crushing it. And if you made a planet bigger than Jupiter, it would be crushed and would have to turn into a star. And so this is a nice way of indicating where stars exist. They exist when gravity starts becoming strong. And you can see that it's about 10 to the 57 times the mass of a proton. Now, the reason I show this picture is that this picture would look more or less the same if you made gravity stronger, except that the scale would be different. The black hole line would go down. And so you could have a small-scale speeded-up universe where gravity was stronger. But it's fairly clear that to have an interesting universe, there's got to be many powers of 10 between the microscale and the scales where gravity is important. And that's why gravity has to be very weak. Otherwise, creatures like us would be crushed by gravity. So a long-lived universe where there's a big gap between the cosmic scales and the microscales requires that there's a very big number. You can think of this as the ratio of the electrical and magnetic and gravitational forces between, say, two protons. And that's about 10 to the 38. And that's that big number. And any interesting universe has to have a very big number like that. But just a proviso, sometimes you read in popular books that gravity is finely tuned. It's not finely tuned, it's just got to be weak. In fact, if gravity was 10 times weaker, you might have an even better universe, because there'd then be even more time, and stars would be even bigger, and animals could get even bigger before being crushed, etc. So there's nothing optimum, but gravity has to be very weak. Second requirement is more matter than antimatter. If the Big Bang was symmetric in matter and antimatter, then as it cooled, you get lots of radiation, but no atoms. There's got to be something which provides a favoritism between matter and antimatter. We have some ideas, I won't go into them further. Also, we need non-trivial chemistry. We need a periodic table. We need this for two reasons. We need it in order to have nuclear fusion to power the stars, and also to allow complexities like us to exist, because if there was only hydrogen, there'd be no complex chemistry, and certainly no organisms. And this requires a balance between two forces: the electric force, which disrupts the many protons in a heavy nucleus, and the nuclear force that binds them together. So this is another case of apparent fine-tuning. And we need to have stars. probably 2 generations of stars, because the first ones make the first heavy elements, and then the second ones can form planets around them because the heavy elements are there already. Also, we need a tuned cosmic expansion rate. We'll start that here. This shows the size of the universe, the rods on the in the Escher picture against time, and the universe expands, and then it goes like this. Now, if the density is too high, then the universe collapses very soon. Otherwise, it may go on expanding forever. And there's an important number called omega, which is the density on average of the stuff in the universe divided by critical density. And the critical density is the one where kinetic energy and gravity just balance. So the universe just has enough energy to go on expanding forever. Now, the actual values are something like this. The ordinary baryons, that's ordinary atoms, about 4% of the critical density. Dark matter provides another 25 or 30%, so we have 0.3 altogether. And so that's enough to give us a universe, in a simple picture, which goes on expanding forever, but decelerating. But we had a big surprise in 1998. It was found that the universe wasn't merely not slowing down very much, it was actually speeding up. So the gravity, which everything exerts and everything else, must be being outweighed by an extra mysterious force latent in empty space itself, which causes an acceleration. And that means that we have, we follow the universe is following something like this. It may have decelerated early on, but now it's accelerating. And this force latent in empty space is a deep mystery. We won't understand it till we understand the granular nature of space on a tiny, tiny scale. And the other thing we need is non-zero fluctuations in the early universe. Because if there were no fluctuations at all, then even now, after 13 billion years, the universe would be cold, neutral hydrogen with no stars and no galaxies. Just very briefly, to think of counterfactual universes, the fluctuation amplitude is about 10 to the minus 5, and that gives rise to galaxies. If you had this number q, which measures the amplitude, if that was bigger, say 10 to the minus 4, you get a universe where galaxies were much bigger. You'd have huge disk galaxies, thousands of times bigger than ours. If it was more than 10 to the minus 3, that wouldn't be so good, because then huge clouds would collapse early on, and you have a universe of huge black holes of violent place. On the other hand, if the fluctuations were even smaller than they actually are, 10 to the minus 6, then we have a sort of anemic universe. The fluctuations might eventually produce some galaxies, but they wouldn't be very dominant. And so this fluctuation amplitude is something which must be within a certain range, between about 10 to the minus 4 and 10 to the minus 5 would be best. So these various numbers, the basic forces, the fluctuation amplitude, etc. So when were these key numbers imprinted? And this is, again, from Max Tegmark, this is a picture how we have the data, which tells us what the cosmological parameters are, the density, and then we theorists turn our handle and try to see what this implies. Well, I want to put up a hazard sign here, because everyone agrees that the answer to the question of why the universe is expanding the way it is, why it's got the ingredients it has, lies very early on in the universe. I said that we can infer back with some confidence to a nanosecond, when the energy of particles was about, that's produced in the LHC, but we now have to go back much, much further still, to the time when our observable volume was squeezed down not merely to the size of our solar system, but to the size of a tennis ball. And I like this picture here, which showed that rather nicely. And this is the era when we believe the universe inflated and when the fluctuations were established. And just to be up to date, then maybe some of you heard that at 4 o'clock today there was an announcement that the fluctuations in the microwave background had a special property which has been determined by a particular experiment, which tells us that in the early universe there were not just density fluctuations, but there were sort of transverse waves, so gravitational waves. And this is an important diagnostic, and this gives us, I think, much better arguments than we had before for taking seriously this huge extrapolation back to when the universe was the size of a tennis ball. That's when quantum fluctuations gave rise to these fluctuations we now see spread across the sky in the microwave background. Now, let's widen our horizon still further. This is the picture I showed again, showing the limits of our universe. And we know that the laws of physics are almost certainly the same everywhere we can see. There's a big debate about whether there might be slight differences, but more or less it looks as though the atoms in those galaxies are like the ones here on Earth. The strength of gravity is the same. But if we ask how universal the physical constants and laws really are, we've got to realize that this domain, the domain we can observe, may be a tiny fraction of what there is. There's a sort of horizon around us set by the maximum distance light can have traveled since the Big Bang. But that's not a real horizon any more than the horizon you see around you if you're in the middle of the ocean is a real horizon. You don't think the ocean necessarily stops just beyond your horizon. And likewise with the universe. And it could be that our universe goes on much, much, much further. Indeed, most people would guess it goes on at least 1,000 times further. That's because the gradient across the part we can see is very small. If you look as far as you can in that direction, things don't differ by more than 1 part in 100,000. But it could go on much, much further still to produce a domain so vast that all combinatorial options are fulfilled, and there's another lecture room somewhere out there with another set of people here. And you will have an avatar, and it may be some consolation that if you make some mistake, your avatar may get things right far away. But that's not all. All this is the aftermath of our Big Bang. And according to some version of inflation, our Big Bang isn't the only one. And here's another cartoon. There's the volume within our horizon. Here are the galaxies far beyond that. But this may be just one bubble, one domain in a universe, cosmos, that's much, much, much larger. And so these different domains, which may or may not be governed by different laws and have different constants, may actually exist. It may be counterfactual, but they may actually exist. And I think one of the key questions that will have to be answered is which part of this decision tree is correct. How many Big Bangs are there? Is there just one, or are there many? If there are many, are they all governed by the same physics when they cool down? Or is there a variety? Do some end up with a different gravity, different repulsive force in space, different atomic physics, etc.? We don't know. But this is something which I think since today I'm more optimistic about being able to settle this, because we now have firmer reasons for taking seriously the very early stages when these conditions were imprinted. But if there was one Big Bang, then that's a brute fact, etc. If there are many, and if they're governed by different laws, then of course we have the possibility that we are not in a typical cosmos, we are in a typical member of the subset in which complexity could arise. And we should bear in mind that many universes may be governed by laws that don't allow any complexity. They're stillborn or sterile, as it were. And to make another historical analogy, here's Kepler's famous picture where he thought that the planets were in orbits whose sizes were related to platonic solids, a beautiful idea. We now don't believe that anymore. And I think we may be due for a similar transition in our thought now. So at the top, planets, we now think that there's nothing special about the Earth's orbit. The Earth is just one planet around one star. All we can say is it's in the temperature range where water can exist. Otherwise, we wouldn't be here. There's nothing more special about it than that. So similarly, our Big Bang may turn out not to be special. We're not in the simplest universe, which would have a zero cosmological constant and exact critical density. We are in a universe that allows complexity to arise, but it may be a typical anthropically allowed model, just as we're on a typical anthropically allowed planet. So our Copernican demotion will go one stage further if we learn not merely that we're on one one star and one galaxy, but we are in the aftermath of just one Big Bang in many. And so the interesting part we want to address is what parts of parameter space allow interesting complexity. I'll jump over this bit. But I want to just finish with this picture, which is, I think, the logo which I would choose for this research area. It's Ouroboros, and it shows the small scales on the left and the large scales on the right. This is the world of the quantum. This is the world of gravity. We know that there are many left-right links. We know the everyday world of people and mountains is determined by atomic and molecular structure. We know halfway up there's a link. Atomic nuclei determine how stars evolve. And higher up still, the dark matter that holds galaxies together is some kind of subnuclear particles made in the Big Bang. But most of science can get by without the unification of the small and the large. This is the domain of quantum, and this is where Einstein holds sway. Chemists don't need to worry about the gravitational forces between the atoms in a molecule, because they are 38 parts of 10 weaker than electric forces. Conversely, astronomers don't need to worry about the quantum fuzziness in the orbit of a planet, because the planet's got so many particles in it. But we do need a unification, and we need it in particular, as symbolized gastronomically at the top here, if we are to understand the very, very early universe, and if we are to understand the nature of space and time themselves. So we have these two frontiers, the very large and the very small. Mostly they're disjoint in their applications, but we need to unify them to understand the very beginning. But before leaving this picture, and before finishing, I want to note that there's a third frontier at the very bottom, the very complex. And the most complicated things we know in the universe are these things. We are complicated, we are very large compared to atoms, we have layer upon layer of structure, but we are very small compared to stars, so we're not crossed by gravity. In fact, we are midway. The geometric mean of the mass of the sun and the mass of a proton is about 50 kilograms, within a factor of 2 of the mass of everyone here, I would guess. And so we are midway, and so we need to understand not just the atoms we're made of, but the stars that made those atoms. And this third frontier, the frontier of complexity, is where 99% of scientists work. And this is a famous picture by Robert Hooke, who was Newton's least favorite colleague and had one of the first microscopes. And I show this because it reminds us that even a flea is far more complicated, far harder to understand than an atom or a star. So it's complexity and not sheer size that makes things hard to understand. And I mention this because I think it's appropriate to end on a modest note. We are hoping that we will have theories to understand fundamental physics and what relates together the 4 fundamental forces. We want to extend unification, which started with Newton, continued through Faraday and Maxwell, and we hope will eventually lead to the synthesis at the top of that picture. But even when that's done, that'll be the end of an important strand in science and a great intellectual achievement, but it'll be irrelevant to 99% of scientists who are working on the frontier of complexity. It won't help them at all to disentangle their complexities. And I think the other nice analogy is with the game of chess. If you've never seen chess being played, you look at some people playing, you can infer what the rules are. But knowing the rules is just the beginning of a long progression from novice to grandmaster. And similarly, what physicists are doing is learning the basic rules and trying to understand them. But even when we understand them fully, then seeing how they apply and how they've led over 13.8 billion years to the chain of complexity growing from atoms to stars to planets and then to a marvelous biosphere, that's an unending quest. And that's perhaps a good note on which to finish. Thank you very much.